Hello, Luke. Welcome to Lesson 94. So today we'll be talking about uniform motion problems again, only with a slight difference. Before, when we talked about these uniform motion problems, they were story problems in which we said, one person left the house and went to the barn um, at such a rate, or it took them a certain amount of time, and then they left the barn and they went back to the house. Okay. And then we found out things regarding rate and time and other things to deal with these story problems. But the issue was in the two journeys that took place, they were always the same distance. It was always from point A to point B, and then maybe from point A to point B again, or maybe it was from point B back to point A, right? But the distances were always the same. Now we're going to switch that up a bit. And what we'll be seeing is we'll see problems where we'll say, okay, we start at point A, and the first trip goes to point B. Okay. And another trip might start at point A. Maybe I'll do it a different color. Another trip might start at point A and go the opposite direction to a point C. Okay? And so clearly, this orange line doesn't have to be the same distance as this black line. So this might be distance 1. This might be distance 2. Clearly, they're not the same distance, or they don't have to be the same distance. Unlike over here, where this distance was always the same as this distance. Okay, nothing changed. The distance was the same. Okay, so that is really the difference in today's story problems compared to other story problems. The other possibility might be that we might have something starting at point A and going this direction. Okay, and then we might have something else starting at point B, maybe here, and going this direction. And the point we're interested in is where they meet in the middle right here. And again, clearly, this orange distance doesn't have to be equal to the blue distance. They could be different distances. Okay, so that's kind of the scenarios we'll be looking at today. Other than that, it's very similar to the other problems that we've been working on. So again, the golden equation here is distance equals rate times time. So important. That is the golden equation here that we will be using over and over and over and over again. All right, so let's get started with an example here, and you can see how this plays out. All right, so we have a southbound train, and it left the city of St. Paul at 9 o'clock a.m. 2 hours later, a northbound train left the same station. If the trains traveled at the same rate and were 360 miles apart at 3 p.m., find the rate of the trains. Okay, there's a lot of words there that we need to work out. So as always, the first step is to draw a picture. So let's do that. So we have a southbound train left the city of St. Paul at 9 o'clock a.m. So let's draw that. So here's their starting point. Okay, this is St. Paul. Okay, and sometimes, I don't know, it might even help to just throw in the time. This is at 9 o'clock. All right. Well, actually, I should write this a little bit differently. We're going to need room. So we're going to put it over here. Here's St. Paul. Here's St. Paul. And this is at 9 o'clock a.m. A.m., if I could write. Okay, and what are we saying? A southbound train. So it starts at St. Paul, and it's going south. So if we think of our compass going downward would be south, so it's going this direction. Okay? And then 2 hours later, a northbound train. So this train left the same station, so it also left St. Paul, but it's not going south, it's going north. So it's starting here, and it's going north. Okay? And it's 2 hours later. So the first one left at 9. This one left at 2 hours later, which would make it 11 o'clock a.m. Okay, so we're just kind of drawing a picture here of what's going on. All right, now what do they want to know? They want to know if the trains traveled at the same rate. So that's important. They're traveling at the same speed. And they were 360 miles apart at 3 p.m. Find the rate of the trains. Okay? So at 3 p.m., let's maybe put that in a different color. Maybe at this point, this is the point that this southbound train is at 3 o'clock p.m. Okay? And then this point here is the point that the northbound train is at 3 o'clock p.m. as well. Okay, so at 3 o'clock p.m., their distance is apart. The distance would be from here all the way down to here, right? That distance is what? It's 360 miles apart. So that distance is 360 miles. See how important these pictures are to kind of illustrate what's going on? So there's 360 miles. That's the distance that these two trains are apart from each other. Okay. All right. So now we've got kind of all this information laid out. We need to pull out some equations here. And what we want to think of is we want to think of our distance equals rate times time formula. Okay. But because we have two trains and everything's different about them, or could be different about them, we really kind of need to organize them in terms of the two different trains. So maybe what I'll do is I'll put train number 1. This will be train number 1, the blue train, the one that left St. Paul at 9 o'clock a.m. and went south. All right. What do we know about train number 1? Let's just kind of get some information out here for train number 1. So train number 1, what we're looking for is, the distance. Let's just plug in this formula. Distance of train number 1, okay, is equal to the rate of train number 1 times the time of train number 1. That's just our distance formula. That's the golden formula right there. All right, so without looking at any of this work, I can say right away this formula applies for the distance, the rate, and the time of train number 1. All right, now what do we know about these three things? Well, the distance of train number 1, we don't really know. They didn't tell us. They just told us that they're 360 miles apart, but that's not the distance. This blue line is the distance of train number 1. The purple line, the 360 miles, that's both distances combined, right? So we don't really know anything about the distance. What do we know about rate? The rate of train number 1. The rate of train number 1 is actually equal to the rate of train number 2, isn't it? Isn't that what they said? If the trains traveled at the same rate. Now, they don't tell us what that rate is, but we do know that rate of the first train is equal to the rate of the second train. So we'll put that down. Okay. And then we know, what about time? Time-wise, we know anything in regard to that? Time of train number 1. Well, let's look at that. So the southbound train, that's train number 1, it left St. Paul at 9 a.m. That's our 9 a.m. right here. And we know that it got all the way to this point by 3 p.m. So how many hours was it traveling? Well, now we need to kind of do a little bit of our time math here. So what's the number of hours between 9 o'clock a.m. to 3 o'clock p.m.? Well, between 9 to noon is 3 hours, right? And then from noon to 3 is another 3 hours. So the southbound train was traveling for a total of 6 hours, right? So the time of the first train is 6. That's a nice number there. All right, and that's really all we know about train number 1. So now let's go on and let's look at train number 2. Train number 2. Let's get some information on him. So again, we know right away that the distance of train number 2 is equal to the rate of train number 2 times the time of train number 2. Okay. Okay. Now, we can say, what do we know about the rate? Well, we know that the rate, we already said it actually, the rate of train number 2 is equal to the rate of the train number 1. That's really the same equation as the one over here. And then what do we know about the time for train number 2? Well, the time for train number 2, he traveled from 11 o'clock a.m. and again, he went up till 3 o'clock p.m. So that's 4 hours, right? From 11 o'clock a.m. to 3 o'clock p.m., that'd be 4 hours. So the time of train number 2 is 4 hours. Okay, so we know that much. All right, so that's kind of just laying out our distance, rate, time for our two scenarios, our two trains. Okay, so now we need to kind of start organizing and getting this all arranged. And there's going to be one equation here that's going to really kind of set us up to solve this problem. So you might consider, this is kind of the illustration. That's our picture. This is kind of all the information that they've given us in the problem. Now, you might say step number 3. So you might even say, this is step number 1, draw the picture. Step number 2, just kind of write down all the information that they give you in terms of distance, rate, and time. And then step number 3 is where we actually start selecting equations to solve this. All right. Now, for all of these problems, and this is important, so if you need to write this down, write it down. For all of these problems, the thing that is going to be pivotal in solving these problems is the distance, understanding the distance. Okay? That is the key to these problems. So the first thing we want to look at is the distance idea here. And what do we know about the distance? Well, they've told us that the total distance is 360 miles between the two trains at the points that we're interested in. So we can then say that the distances, I'll do this in purple. The total distance was 360, and that's the total distance. So that's the distance of train number 1 plus the distance of train number 2. Okay? So again, we're concentrating on distance. Distance of 1 plus distance of 2 is going to be equal to 360. Now, here's another point that we need to recognize and remember, because we'll be doing this on pretty much all these problems. We first write down how we see the distance. Distance 1 plus distance 2 equals something. Okay? Now we need to translate the d's into rates and times. Okay? And we can do that in our heads, but if you need to make sense out of it, notice up here that we said already that distance 1 is equal to rate sub 1 times t sub 1, and distance 2 is rate sub 2 times t sub 2. So what we're going to do is we're going to replace this distance 1 with r sub 1 times t sub 1, right? I'm just using substitution. D sub 1 is equal to this, so we're going to just cross out the d and put in the r sub 1, t sub 1. Okay? In like manner, we're going to do the same thing with the d sub 2. Instead of saying d sub 2, we're going to translate that into rates and times by substituting in r sub 2, t sub 2. R sub 2, t sub 2 is equal to 360. Okay? Now, once that's done, we can ignore this problem. We are done with this equation. All we've done is just rewritten it here in this form. All right? So it's so important. I'm going to say it again. You start by looking at the distance. Try to come up with some sum of distance equal to something. Once you've done that, replace the distances with rates and times. Okay? Once you've replaced them with rates and times, now really what we're trying to do here is we're trying to get a system of equations going. All right, so that we can solve for all of these variables. And how many variables do we have? We have 1, 2, 3, 4 variables, 4 different variables. So we need 4 equations here, and they all have to be using one of these variables. So let's look at our information that they've given us. Now we've already used this one, and we've already used this one, so we're not really going to worry about those. Let's look at the other ones now. So we have, what can we say? R sub 1 is equal to R sub 2. That's a great equation. R sub 1 is equal to R sub 2. So that's another equation that we can use, and I could have pulled that from either one of these lists over here. This one and this one, they're the same thing. All right. Then I've got t sub 1 is equal to 6. Well, t sub 1 is another one of our variables here, so we can use him as well. That's equation number 3. We're up to 3 equations. And then I've got t sub 2 is equal to 4. Well, that's great because, again, t sub 2 is in here. That's one of our variables. So t sub 2 is equal to 4. And bingo, I've got my 4 equations. Okay? Now, once I've got my 4 equations, now I can go ahead and solve this using regular methods. All right, and this one is pretty straightforward. We just kind of substitute in. So if we start with that first equation, maybe I'll go to black here. R sub 1, well, we know that R sub 1 is equal to R sub 2. So I can replace that R sub 1 with an R sub 2, right? R sub 1 is equal to R sub 2. Just plug it in. T sub 1, we know that's a 6. So I'm going to write it out in front here because I like my coefficients out in front. 6 times R sub 2. Then I have my plus. Then I have R sub 2, which we don't know. I mean, I could say it's equal to R sub 1, but I don't want to do that. I want to keep it as R sub 2 so that I have only one variable going on right here. They're both R sub 2. And then I have T sub 2, which is a 4. So again, I'm going to write that in front. 4 times R sub 2. Okay? Equals 360. Now I can just combine these, and I get 10 R sub 2 is equal to 360. Divide both sides by 10, and I get R sub 2 is equal to 36. All right, so what is R sub 2? That is the rate of the second train. So the second train was going 36 what? 36 miles per hour. Okay, now what did they want to know? They want to know, find the rate of the trains. So that's only the rate of the second train. Let's find the rate of the first train. So let's plug this R sub 2 into this equation, right? R sub 2 is equal to 36. Well, then R sub 1 is also equal to 36. And actually, we already knew that, right? Because they said that the rates were the same. So there you go. The rates of both trains are 36 miles per hour. Okay? All right. I know it's a bit involved, but it's really not too bad. You just kind of have to develop a process. And I think the easiest process to go through is first, always, always, always draw the picture. That's the first step. Draw the picture with as much detail as you can. All right? And then the second thing is really just to take the two items that we're talking about and just write down all the information that you can given what they've given you in the problem. And then the third step is to write that distance. Distance plus distance equals something. All right? We're kind of summing those two distances up. All of these problems are going to say something about the total distance. And that's what we're really interested in. So find that total distance and write this problem, this equation. D sub whatever plus D sub whatever is equal to something. And once you have it in that form, just remember that D's, all the D's can be replaced with R times T. All right? And then once you've reached this equation, right here, once you've got that equation laid out, it's not so bad after that. You're pretty much just copying down other pieces of information that you've gathered up at the top so that you can get 4 equations with 4 unknowns, and then it's just solving using usual methods. Okay? All right, so that's how it works. So let's try another one here. A train leaves St. Paul at 10 a.m. and heads for Duluth 180 miles away. At the same time, a train leaves Duluth and heads for St. Paul at 75 miles per hour. If the trains meet at 12 o'clock p.m., what is the rate, oh, that's a typo, for the first train? Okay, all right, so let's think about this. Tell you what, pause the video. Try to draw a picture of this. Don't worry about the rest of the problem. Just draw a picture, and then we'll draw one together, and I want to see, or I want you to see how close you came to getting the correct picture. So pause the video and try that. Okay, so how did you do? A train leaves St. Paul at 10 a.m. All right, so here's St. Paul. Once again, here's St. Paul, and we'll call it St. Paul. Okay, and this is at 10 o'clock a.m. Okay, and it heads for Duluth. Well, so that Duluth is north, so we're going to say it goes this direction, up to Duluth, 180 miles away. Okay. And actually, that's kind of a long arrow. I'm going to move this down here a little bit. St. Paul is here. Okay, so it heads north. Ugh. get a straighter line here. It heads north. Okay? All right. And then Duluth is up here. We'll call this Duluth. That's where this train is headed. Notice it didn't say it made it to Duluth. It's just headed towards Duluth. Okay, so that's why I'm not completing this arrow all the way up. It's headed towards Duluth. And Duluth is 180 miles away. So let's just write that in here. So from here down to here, this is 180 miles. Okay, from Duluth to St. Paul. Now, at the same time, a train leaves Duluth. So let's get a different color going. A train leaves Duluth, and where's it going? It heads for St. Paul. So it's going this direction. Okay? And it's going 75 miles per hour. So that's great information. It's going 75 miles per hour. Okay? If the trains meet at 12 o'clock p.m. So they meet right at this point. This is where they meet. And they meet at 12 o'clock p.m. Okay? What is the rate for the first train? So the first train is going to be this one, the one in black. Okay? The second train is the orange one. So they want to know what's the rate of the first one. Notice they gave us the rate of the orange one. All right, so there we go. That is our picture. So how did you do? Were you pretty close to that? Hopefully you were. If not, look at this closely, see how you drew it, and try to understand where you were maybe wrong. Now, you could have written this in different ways. Maybe you went, horizontally. That's whoops, that's terrible. That's fine too. I mean, I went north and south because I knew that Duluth is north of St. Paul, but if you didn't know that, maybe you put St. Paul here, and maybe you put Duluth here. That's fine too. It doesn't have to be accurate as far as up and down or left to right. But the guts of the problem should be the same. Okay? All right, so now we're done with step number 1. Remember, this was step number 1, draw the picture. Let's move on to step number 2. So step number 2 is what? Step number 2 is we're arranging all of our information, right? So let's take our orange, and this will be, now we have to get some variables going here. So the second train, we'll go second train because that's, what we said, that was the second train here. So second train, what information do they tell us in terms of distance, rate, and time? Well, right away, without even looking, we know that distance of the second train is equal to the rate of the second train times the time of the second train. That's automatic, all right? Now, what do we know in terms of the rate? Do we know the rate? They don't. Oh, yeah, they do. They tell us the rate is 75. That's great. Okay. Time. Do they tell us anything about the time of the second train? Well, it's at the same time a train leaves Duluth. So actually, I could have put that up here. He left Duluth at 10 o'clock a.m. as well. Same time as the first train. Okay. So at the same time, he travels from Duluth and heads for St. Paul. And it says that they meet each other at 12 o'clock p.m. So from 10 o'clock a.m. to 12 o'clock p.m., what does that mean? That means that the second train has been running for 2 hours. So the time of the second train is 2. And there we go. So we got some really good information there on train number 2. Now let's look at train number 1, which is the black train. So train number 1, we can just automatically say that the distance of train number 1 is equal to the rate of 1 times the time of 1. And now what do we know about the rate of train number 1? Well, we don't really know anything about it, do we? They don't really tell us anything about the rate. They don't. They don't say anything about it. So this is just a question mark. We have nothing on the rate. All right. What about the time? The time of train number 1, well, it's the same, right? Because it started at 10 and it went till noon. So it's going to be also 2, just like train number 2. So there we go. There's all of our information from the problem. That's step number 2 done. Now we move on to step number 3. And recall, step number 3 is where we deal with distance. So what can we say about the distance of these 2 trains and their trips? Well, we know that the distance of the first train and the distance of the second train, they have to add up to be this 180 miles, right? This plus this has to be 180 miles. That's the total distance between the two cities. Okay, so we know that distance of train number 1 plus the distance of train number 2 has to be 180. So there, we've figured the distance equation, but now we need to replace the d's with rates and times. So d can be replaced with, well, r1, t1. So the rate of 1 times the time of 1, plus d2 can be the rate of 2 times the time of 2, equals 180. And then that means this one can go away. We're done with that. Okay? So now we've got one equation, but we need 4. So let's look through our information. We've already used these two. Let's look through our information now. What else do we have? R2 is equal to 75. That's good information. T sub 2 is equal to 2. So that's good information. We're up to 3 equations. R sub 1 doesn't help us at all because we don't know anything about it. But T sub 1 is helpful. T sub 1 is also equal to 2. So we can write that as well. And thankfully, that gives us what we need. That gives us 4 equations and 4 unknowns. So now we can go ahead and solve this. So the R sub 1, we don't know what that is. That's the unknown. T sub 1, we know that T sub 1 is a 2. So I'm going to write that out in front. R sub 2 is 75 times T sub 2, which is 2, equals a 180. So then we have 2r sub 1 plus 75 times 2 is 150 equals 180. I can subtract the 150 from both sides. And then I'm going to get 2r sub 1 is equal to 30. Okay. And then I can divide both sides by 2. And r sub 1 then is going to be equal to 15. So the rate of train number 1 is 15 miles per hour. And that is, in fact, what they wanted to know. They wanted to know what is the rate for the first train. So the first train is traveling at 15 miles per hour. A lot slower than the second train. Okay? Very good. That is the process. All right. So let's try another problem here. It's kind of dealing with the same thing. Why don't you go ahead and read this one through and try it on your own this time, the whole thing, and then we'll do it together. So the ships were 500 miles apart at noon and were headed directly for each other. They collided with each other at 9 o'clock p.m. Find the speeds of the ships if one was 30 miles per hour faster than the other one. All right, so let's see if we can figure this out. First, again, the first step is to draw the picture. So we begin with that. Number 1, let's draw the picture. So we've got the ships being 500 miles apart at noon. So they're kind of jumping right away to saying, okay, here's ship 1, okay, and then here's what color? We'll go black. Here's ship 2, okay, and then the distance that these are apart from each other is 500 miles. All right, and well, this is kind of the position at noon. So this is at 12 o'clock and 12 o'clock. All right, okay, so that's kind of the first piece of information. And they're headed directly for each other, so that's interesting. So we've got this one that's going this direction towards the other one, and then we've got the second ship that's now going this direction and towards this guy. So they're headed right for each other. Okay, and then they collide. They collide with each other at 9 o'clock p.m. So at this point right here, they have a collision, and that's at 9 o'clock p.m. Okay? All right, so find the speeds of the ships if one was 30 miles per hour faster than the other. All right, so this is kind of our diagram of what's going on here, right? Now let's go to our step number 2, which is to actually kind of pull out any information that they give us. So we have our variables, and we'll call the first ship. So we'll call it, yeah, so we'll call it ship number 1 for the first ship. Okay, so what do we know about the first ship? Well, let's do the distance equals rate times time. So we know that the distance of ship number 1 is equal to the rate of 1 times the time of 1. What do we know about the rate of ship number 1? Well, we could know something. It says here that the ships, one of them was 30 miles per hour faster than the other. They don't tell us which one was 30 miles per hour faster than the other. So we get to kind of pick. It doesn't really matter so long as one of them is indeed 30 miles per hour faster. So let's just make the faster one to be ship number 1. Okay? So then in that case, his rate, the rate of ship number 1, because he's 30 miles per hour faster than the other one, he's going to have the rate of ship number 2, all of the rate of ship number 2, plus an additional 30 miles per hour. All right, so that is the rate of ship number 1. All right, now what about the time of ship number 1? Well, the time that we're interested in is the time that he is sailing up until the collision. So he started at 12 at noon, and then he collided at 9 o'clock p.m. Okay, so if he collided at 9 o'clock p.m., how many hours is that? That's 3 hours. So his time is 3 hours. And actually, I won't put hour. I'll just put 3. There we go. Okay, and then that's kind of all of the information that we can get for ship number 1. Let's go to ship number 2. So what can we say about him? Well, right away, we know that his distance is going to be equal to rate times time. And what do we know about his rate? Well, all that we really know is that he's 30 miles per hour slower than the other one. I guess I could create an equation out of that if I wanted to. I could say that his rate is going to be equal to the rate of ship number 1 minus 30 miles per hour, because we said this ship number 1 was 30 miles per hour faster, so ship number 2 is 30 miles per hour slower than ship number 1. So I could write an equation for rate, the second ship's rate, like that. All right. Then what about the time? Well, the time is actually the same, right? Because they both started at noon and they collided at 9. So the time is still 3 hours that he was sailing. All right. So there's all of our information for ship number 2. And that really finishes up step number 2, right? Because that's all the information. Now we need to look at some equations. So what are we going to do? Well, let's think about, and this is step number 3, let's think about the distance like we've done before. So what can we say about the distance? Well, we can say that distance of the first ship plus the distance of the second ship is equal to what? So think about that. The distance of this first ship plus the distance of the second ship, that's going to be the 500 miles total, right? It's the total distance. So the distance of 1 plus the distance of 2 is equal to 500. And as we've done in the past, we're going to change these d's to rates and times. All right, in a sense, we're just using these first equations up here and plugging them in for the d's. So we have the rate of 1 times the time of 1 plus the rate of 2 times the time of 2 is equal to 500. And then we can kind of lose this equation. And we're actually done with this equation. We're done with this equation. Okay. All right. So now, once again, as we've done on the previous problems, we're just at this point trying to build a system of equations. So we need 4. We have 1. Let's look through our list. We have this equation. R1 is equal to R sub 2 plus 30. It's a good equation. We're up to 2 equations. And I have T1 is equal to 3. That's another good equation. Now be careful with this one, because you might be tempted to say, okay, well, I can use this equation. R2 is equal to R1 minus 30. But watch out, because this equation is actually the exact same equation as this one. Okay, these two are the same thing. think about it. If I were to rearrange this and solve this for R2, what would I do? I'd subtract 30 from both sides, and I'd end up with R2 is equal to R1 minus 30. Well, that's exactly what this is. So they're just different versions of the exact same thing. So we can't use the exact same equation. That's not going to help us. We need different equations. So since we used this one over here, we really can't use this one either. All right, and then that leaves us with the final equation right here, which we're going to use. So t sub 2 is equal to 3. Okay, so there we go. We have our system of equations. Now we can go ahead and solve using our regular methods. So if we plug in for R1 is, according to this, R1 is R2 plus 30. So we have R sub 2 plus 30 plugged in for R1 times T1, which we know is 3, plus R2, we don't know what R2 is. That's our variable. T2 is 3. Well, I guess I'll put it here. Is equal to 500. Now we can do some multiplying out here. So we have 3R2 plus 90 plus 3R2 is equal to 500. Okay, and we combine our like terms, and then I'm going to subtract the 90 from both sides, and we end up with 6R2 is equal to 410. And then if I divide both sides by 6, I end up with R2, so it's 68 1/3 miles per hour. All right, so there you have it. The rate of the second ship is 68 1/3 miles per hour. Moving pretty fast on that ocean. Okay, and now if we go back to our question, what do they want to know? They want to know find the speeds. So that's one speed. What's the other speed? We need to figure that out. So let's plug that in. We're going back into our equations. If R2 is 68 1/3, then R1 is going to be equal to 68 1/3 plus 30, right? All right, so then R1 is going to be 68 30 is 98 1/3 miles per hour. So R1, the faster ship, remember we said he was faster by 30 miles per hour, he's going 98 1/3 miles per hour. R2 is going 68 1/3. These ships are really moving on the ocean. All right. Very good. So that is the solution for this problem. Now, hopefully you got that on your own, but if you didn't, make sure you look through this, you understand what you did wrong so that you don't do the same mistakes on your C work. All right, well, we'll stop there, and good luck, and I will see you tomorrow.